Welcome to this explainer. Today, we're diving into something really exciting, a bold new publication in the journal Nature from D-Wave that could literally redefine the entire quantum computing race. You know, the industry's massive bottleneck has always been error correction, but what if the solution isn't about preventing errors entirely, but simply making them incredibly obvious when they do happen? Before we break down the complex mechanics of D-Wave's new hardware, consider this core question. What if the secret to building a better quantum computer is just knowing when it's lost something? That single powerful idea drives D-Wave's entire strategic pivot, and honestly, it might just be the exact shortcut the industry has been searching for. So here's how we're going to map out this fascinating shift today. 1. D-Wave's quantum pivot. 2. The dual-rail difference. 3. The entanglement breakthrough. And 4. The road to 2028. All right, let's jump right into Section 1. D-Wave's quantum pivot, from annealers to gate-based hardware. D-Wave has always been a bit of an outlier in the quantum space. For years, their legacy was all about quantum annealers, machines designed to solve very specific optimization problems. But now, well, D-Wave is officially taking on the industry giants by pivoting to general-purpose gate-based hardware. They're aiming to build a quantum computer that can theoretically solve absolutely any problem you throw at it. It's a real game changer. To pull off this massive pivot, D-Wave acquired a startup called Quantum Circuits, which originally spun out of Yale University. This move allowed D-Wave to focus entirely on a highly unusual technology called fluxonium, or the dual-rail qubit. It's this fascinating approach that promises to dramatically simplify the biggest headache in all of quantum computing. Which brings us to Section 2, the dual-rail difference, simplifying error correction. So, what exactly is a dual-rail qubit? Well, it's also frequently called an erasure qubit. Think of a super fragile quantum data state. But instead of the data silently flipping or getting corrupted without us noticing, its outright disappearance acts as an immediate blaring alarm bell. Basically, if the photon escapes, if it's erased, it's instantly obvious. That missing data flags an error right away, which drastically reduces the need for those incredibly resource-heavy error correction codes. The physical setup for this is actually remarkably elegant. First, you link two resonators together, let's say a left one and a right one. Next, you just drop a single photon into the system. To actually function as a qubit, that photon can be measured in the left resonator, the right resonator, or, because it's quantum mechanics, right, it can exist in a superposition of both left and right simultaneously. Now, in a dual-rail system, the overwhelming majority of errors are just photon loss, or erasure. The photon simply escapes the hardware. And like we said, this is easily detected without needing a bunch of extra qubits just to run some complicated error correction code overhead. The next most common error is a phase flip. And a bit flip, that's a very distant third. We're talking practically non-existent, down at the 10 to the minus 6 level. Because those harder-to-detect errors are so incredibly rare, D-Wave can use a much simpler, more compact error code. This lets them achieve useful computation with way less hardware. Moving on to Section 3, the entanglement breakthrough, testing the tech in nature. Now, it's one thing for a single qubit to safely hold its data in isolation. But a real quantum computer needs to perform operations. It needs to entangle qubits together. The immense risk here is that forcing qubits to interact usually ruins that fragile state and introduces a bunch of messy errors. But D-Wave set up two dual-rail qubits separated by a tunable coupler, and they proved they could successfully entangle them. How? By simply activating the connection, letting one qubit partially occupy the coupler to interact with the second one, and then just shutting it off. And the sheer speed of this operation is absolutely staggering. The total entanglement process took a blistering 500 nanoseconds. The actual wait time while the coupler was active was a mere 200 nanoseconds. To put that into perspective, that is significantly faster than the time it takes you to even glance down at your watch. These ultra-fast operations mean there is way less time for the environment to interfere with that fragile quantum state. But believe it or not, speed wasn't even the biggest victory here. As D-Wave's Trevor Lanting emphasizes, the fundamental excitement around this Nature publication is that it actually preserves the error hierarchy. This is massive. It means that even during these lightning-fast entangling operations, photon loss remained the dominant error, roughly 5 times more common than anything else. Entangling the qubits didn't suddenly introduce a flood of those awful, hard-to-detect bit flips. Their shortcut to error correction completely survived the entanglement test. And that leads us to Section 4, the road to 2028. facing the reality check. While the Nature paper is incredibly promising, it also honestly acknowledges the current limitations we're facing. First, as the number of gates increases, the devices showed rising error rates. They saw an unexpected, roughly quadratic decrease in fidelity, which is likely due to calibration drift over time. Second, while detecting photon loss is fundamentally easier, D-Wave still needs to perfect mid-circuit erasure detection. They have to actually catch that missing photon while a calculation is actively running, not just check for it at the very end. And third, they really need to develop the classical computing theory necessary to interpret the massive data streams of error information coming off the processor. So the theoretical foundation is definitely validated, but the massive engineering challenge, that's really just beginning. To push past these hurdles, D-Wave has set a highly concrete target for the near future. They want to scale this technology up to 181 dual-rail qubits by the year 2028. Why 181 exactly? Well, because that specific scale should provide exactly enough qubits to rigorously test several forms of the surface code error detection scheme in real time. If the hardware performs as expected at that scale, the next logical step is linking enough of them together to host hundreds of logical, fully error-corrected qubits. So, we'll leave you with this final thought today. If knowing exactly what you've lost is half the battle in quantum stability, will D-Wave's missing photon shortcut to error correction be the key that finally unlocks practical, general-purpose quantum computing by 2028? It's a massive bet on a very unique architecture, and for sure, the entire tech world is going to be watching closely to see if this dual-rail revolution stays on track. Thank you so much for joining us for this explainer, and keep your eyes on the quantum horizon.